Okay, so I think we're recording, right? Okay, so yeah, we should be recording, I think. Yeah, recording. Okay. All right, let's begin. All right, so today we should conclude, hopefully, the theory on transformers, right? So we were discussing GPTs. So I'll wrap that up, guys. So I'll wrap up GPTs today. And then, so I think we're kind of like in the middle of the code, right? So we'll go over that. We'll go over encoders, BERT models, give you the contrast basically of just a general ideas, okay? I also did get the instructions for the Scholar GPUs. So for those of you that don't have a GPU, right, for your assignments. Okay, so I'll go over that today. So I'll start with that actually, probably. You don't need to follow along per se, because then it'd be like 20 people trying to get a GPU from the queue and not all of you will. Okay, so remember, this is only for homework assignments. It's not really going to work like for in class. You know, it just, it's never worked. We just don't get enough GPUs. In fact, you guys will get a GPU. I won't get a GPU. It's how it works. So I gave up on trying. All right, so we are recording here. So the idea is, I loaded a guys over there. Guys, can you be quiet, please? The both of you. All right, so I loaded a document here in 530. I'll show you some of the main issues with Scholar. It's great, but also finicky. So this won't take too much. I'm not gonna do like a code demo or anything like that. So I added this document, right? Troubleshooting GPU Scholar. You can click on that. At the very bottom, basically this is like how I know how to connect to this. And then I'll show you some of the things that you can do. There's various things you can do. So there's this link, the Gateway Scholar. So you can copy that. Copy. All right, then you can open up a browser. And I'm logged into Brightspace, so that basically means I should be logged in to this as well. Okay, so this is how it works. Then what you do is, and that's in the instructions in that document. So basically, I'm just following the steps here in this paragraph. So you would go here to interactive apps. And then there's Jupyter Lab from DataMine. That's a thing that they have at West Lafayette. So that's not it. So you can pick on Jupyter Notebook here under GUIs. So it's GUIs, you pick Jupyter Notebook. And then here is basically the queuing system. So as you can see, you can request a GPU, okay, like that. And you get a maximum of 4 hours. So keep that in mind. There are limits, unfortunately. Okay, so certainly for the first homework, you'll have no issues. For the mini project, just try to constrain it to that. Otherwise, you could do something like you save a checkpoint, load from that checkpoint, keep training for 4 hours, save the checkpoint, load the check. I mean, you can do that. All right, so unfortunately, but it's the best that, so as I said, I understand we have constraints, so you got to build the best model that you can with what we have. So here is the number of cores. That should not be an issue. Number of GPUs. I believe you can select up to 2 if you're doing multiple GPU, although none of you are going to be doing that, I don't think. And then the type of GPU, basically you could select, but you can just pick first available, and at least that way you get one sooner. Okay, then you can leave this one, use Jupyter Lab instead of Jupyter Notebook. I'm just going to use Jupyter Notebook. And then you would basically click launch. And See, it says be patient as your current job currently sits in queue. And the wait time depends on the number of cores as well as, but apparently one became available, one GPU became available. Okay, so I'm waiting for a link. You can see there's a timer there, 1 hour and 59 minutes. So you got 2 hours for what I requested, and you should have the GPU during that time. So at least for the first homework assignment, you know, do this. So then here you have this blue button here. So you click on connect to Jupyter and it takes you here. So it took me to the desktop and then it took me to here. So basically it looks like, you know, Jupyter notebooks, but it's running on a GPU. Okay. You can do some checks if you'd like. So for instance, I have this script that I was playing with. So basically I was doing using transformers to fine tune a project. Okay. And so just to kind of illustrate it, you know, the basic mechanics, I will show you there's a few things to keep in mind. You get a space of 25 gigs is your quota. If you exceed that by saving too many checkpoints, you're going to run out of the 25 gigs and your program will die, right? Because it's going to run out of memory, space. So that's an issue. I understand there's a scratch. They call it space that might be 1 terabyte, but you got to figure out how to get to it, okay? But otherwise, this default one is 25 gigs. You know, these models are big, right? You download it once and that's half a gig already, right? So does that make sense? So you got to watch that. I'll show you how to look at the quota and everything, but I'm just saying keep this in. There are these constraints. I think you have a total of 250 files for some reason, and then maybe, but I know that 25 gigs is a thing, although there is another storage space. I just haven't found it. So if you find it, let me know how to get there, okay? I'll go over some GPU commands just to so that you can check always. So we're going to go to the GitHub here. All right. And under the GitHub, I added some under the transfer learning. I added here in Hugging Face. I think under intro. Well, it was already here actually, but I have some commands here just to check the GPU basically. All right, so there's a few commands like NVIDIA SMI, you want to look at that one, but also here you can just try these out. So I'm going to go back here. And paste it in there. So Torch CUDA is available, so let me run that one. Okay, so CUDA is available, so it's true. Okay, so these are just things that you can do just to check that you've gotten the right. Maybe you're just like not sure, right? So you can try these out. There is this one, device count, how many CUDA cores. There you go, 1. Which device it is, it's usually device 0. Okay, device 0. You want to look at that it's a, you know, what type of a like object. It's a Torch CUDA. So CUDA device 0, what is it? So it tells you it's a Torch CUDA device. You might want to know what the name of it, like it's a GTX 950 or something like that. And you can see this is a Tesla V100 GPU. Okay, so just I have an RTX 2080. I know it's about 80% the capacity of this one. So it's not like this is 100 times better than the regular ones. Okay, but these are, you know, more like the university ones. I don't know how many they have. I think they have like 16 maybe or 32 GPUs. So if you don't need a GPU, don't request a GPU, right? That's basically what I would suggest. But whenever you're running in like, you know, when you're training the first GPT, you can certainly now, if you haven't done so already, take that code, take your data, and start running it through here. Does that make sense? So you have now the tool. Again, you know, look for hours where you think people may not be using it that much, because you gotta be. But the thing is, though, once you have a GPU, then you can start working on it. I think you can schedule as much as 4 hours. Debug it on the CPU, have everything ready. Once you think it's good to go, then just launch the job on your Scholar. Does this make sense, guys? This basically should be it. You see you have a GPU under there, and then the code that I provided has everything it needs to run on GPU, right? So it checks to see if you got CPU or GPU. If a GPU is detected by looking at is available, it'll just switch to GPU. So you don't have to worry about changing the code in any way. You just worry about loading the data, basically. Any questions? That's it. This is Scholar GPU. All right, a few things, few issues about it. So let me see. I go back here. I need to start. You can start a terminal. And in the terminal, you can look at certain things associated with your accounts. So I believe the terminal is here. Scholar Shell Access. You can click on that. And basically, you have this terminal. You can see already it's got a few commands in there. It says your quota is 250 gigs. Yeah, I don't know. It might be the scratch. See, there it is, the scratch. And I think there's a default one that's smaller and it defaults to that. Okay, so I haven't figured that out yet, but I do recommend if you're going to be using this, figure this out really quickly so that you have more space, because I've run into this problem that I'm in the middle of a job and I just fill up my quota. Okay, so definitely spend some time. I thought it was 1 terabyte, but apparently it's 250. Oh, it's 250,000 files. Okay, that makes more sense. And then 250 gigs for this, but as I said, scratch. Some commands are QList, and that's explained in the document. And also another important, well, there's the user guide, so maybe read through that. Might save you some time later when you're running into problems. And then there's the other command is my quota. So here we can see you have FE001. So let me clear here. You can do here my quota, I believe. Yeah, and it's gonna print basically how much you have. So you can see, I see here I have a terabyte. It might be because I'm professor or something and I have a little bit more. But anyway, if you can work in the scratch and load your models there, you'd have about 250 gigs. Otherwise, you're limited to 25 gigs. You can see I'm at 15, and just running a script, I really quickly fill this up. Okay, just with one. And your mini project is big, right? So it will have a lot of download a lot of files, etc. So keep that in mind. Does this make sense, guys? So you can take a look here at your quota and just make, that's one of the main issues. I don't think RAM will be an issue or GPU memory will be an issue. If you run into those, let me know. There is another command. I didn't try this one. This works on my computer, NVIDIA SMI. Yeah, so I'd have to check. It runs on my GPU. I don't know if you guys have tried this one on those of you that have GPUs, but not everything that runs like normally in a computer is available in Scholar. But you might be able to check the documentation to see if you can install some of these things. Okay, you can install certain things, and that's in the documentation. Does this make sense? And then obviously the regular Linux commands apply. No such. Oh, yeah, sorry. Right, so you can see what you have in here. Basically, I'm in my user. If you exit out of here, you're going to end up in everyone else's space, right? And there's 23,000 users or something. All right. So anyway, I showed you this. You can see basically it's just a regular Jupyter here. And this is basically where you can run your applications. I was just trying out something, just I guess just to show you. It's just basically the, like you have to install. Okay, yeah. So you have to install things. So if like something is missing, it's the same approach. Just do pip install datasets, pip install transformers. It should work. Okay. Sometimes you have to exit out and then come back when you do a pip install. It may not like update it, but if you exit out, it should be there. Here I have where's the yeah, so from data set, so I already installed this, so you can see. Okay, so it's thinking. It ran, and this ran on that V100 GPU. Okay, we can take a look at the shell over here. My quota was at 14.9. Okay, still at 14.9, but let's do an experiment of what I'm telling you here. So we're going to go through an example. This is just a fine-tune example from Hugging Face, very similar to what you guys are doing in the mini project, right? Remember, in the homework you're just pre-training, but in the mini project you're fine-tuning. So then we, download a data set here. Okay, import some libraries, and we're gonna, basically like we did with the GPT, we're gonna convert the data into IDs. So there's the data. Here's the two models, right? Just like before, you download GPT-2 as your model checkpoint. You need a tokenizer, so you can go ahead and do that. Okay, those are just the names. Here, auto tokenizer is going to download the tokenizer. Okay, so it's thinking. It did it. All right, let's check the shell. Okay, 14.9. Okay, I like it. All right. All right, so let's keep going though. Then, this is tokenized data sets, right? So there it is. Okay, starting to process. Okay, good. You can see now the data has been tokenized. This is very much like the from scratch code, right? Same idea. Block size. Now this is going to group the text very much like shifted, but input and output. Same idea. Okay. All right. So see this, processing is happening. Take a look at the memory usage here, or hard disk space. 14.9. Okay, so far so good. I think it's because I already have those data sets, right? But when you start training, you start creating the checkpoints and everything, and that's where the problem might happen. Yeah, please go ahead.
My quota under the project said 0 gigabyte.
When you type my quota?
Yeah.
All right, hold on. I'm going to type it. Yeah, go ahead.
You have it there in your name.
Where you see your name here? Yeah, what do you see here? Limit says 25, right?
No, it's 0. No.
Really?
Yes, it's 0. Even here. It's 0.
What about on the scratch one?
It's 0, yeah, 0, 0.
Well, you should have space. I mean, right? I didn't set this up. I mean, okay. So yours, that's interesting. Limit is 0 there. 0 gigabytes, it says.
0 kilobyte.
0 kilobytes. Well, maybe.
I mean, the size is 300 megabytes.
Where? What size? In home here.
Yeah. Then under site, just the site,
Mhm.
it said 328 gigabyte. and then
Well,
added-
I don't know honestly, but let's assume that you just haven't activated it or something, or if someone knows what.
I have the same thing. My size is 7 gigabytes, because I ran the example, but my limit is 0 kilobytes.
Yeah,
Really?
so. Just do it.
So you have, so that, I take that to mean that you have no limit then. Right, so, yeah, that's good. I mean, I guess well, there you go, then I need to call them and see why they're limiting me. Yeah, go
I
ahead.
also don't have the depot, the bottom one.
Yeah, this one is, it's Civis, so this is just like other work. But you do have these two, correct? For the Scratch, do you have 1 terabyte?
Says limited 0 kilobytes and size is 0 kilobytes.
Okay, I will have to ask. I don't know, honestly. I assume you all, keep trying, but read the documentation. Maybe it says something there. And I will ask that question. Okay, but just keep in mind, for me, it's been an issue actually that I filled it up. So I'm just running through this example kind of just to show you that, what you can do. So you can see here, now it's getting from pre-trained model and the config, right? Okay, it ran that. Now I already had these, so they're probably still okay with 14.9 gigs. Okay. Then training arguments here. This is the training argument where you create this checkpoint. So this, when you use this, the training arguments for the trainer, right? And this is kind of how Hugging Face works, right? So it tries to simplify everything. And so basically you have configuration arguments where you have your parameters, and then you have this trainer. And then the trainer, notice you give it the training arguments, the model, the data sets basically, and that's it. Right? And so this is a folder where you're going to save your data. Okay, and I did, some default parameters. Okay, so let's take a look at this. See, when I run this, the trainer.train, it'll start training. This is the training process for this example. This is just a simple fine-tuning. It's like the hello world of fine-tuning of Hugging Face. So let's take a look at the shell here. Okay, 14.1. Maybe I'm just crazy and it's gonna work this time, but this has given me trouble before. Okay, so it's doing the training. At some point, it will save a checkpoint. Okay, and also here you can see how many hours you have left. So in this case, 1 hour and 41 minutes is the timer. So you got to do your job within the allotted time. So as I said, basically, if something will take you more than 4 hours on a GPU, save a checkpoint, read that checkpoint in, do another 4 hours. You'll have to kind of plan it out that way. Okay. But it should be doable. Let's go back to the Jupyter. Yeah, so it's even on a GPU, as you can see, this can take a little bit. So you can imagine if you were using a CPU, this would not be fun. Okay. Questions so far, guys? Is it making sense how it should work? At least for the first assignment, I don't think you'll have any problems. That train in an hour, it's basically all the books of Shakespeare or something like that, I would think, right? Yeah. And so that should be enough for the homework. Have all of you finished that homework assignment by this point? Or have started at least, right? And now you have the GPU, so you should be able to finish it. So maybe by next Wednesday, we can do the presentations. Does that work? Clear? All right, so I'll create the link on Brightspace And basically that homework assignment will be due a week from today, right? The first homework, just using the pre-trained code on the GPU with a whole bunch of books, and let's see how it works. So you can use that Huck Finn code that I posted. That's probably the best one because you can actually ask it questions and things like that. All right, and then we'll schedule like the last half, the second half of class, where you guys can come up here and do your presentation. Nothing formal, just, you know, and you don't have to run it in real time. So you just have like a PDF or something. Okay. All right. So yeah, so it's doing this, and while it's doing this, it's creating the checkpoints. So let me run the my quota here. See, it went up. You see that? Now it's at 17.7 and it's not done with the training. If I do ls-l, it's creating those checkpoints. Okay, so there's a way to see where they are. If you go here, I think. Yeah, so here's somewhere. You can see all the files. Here it is. So you see this GPT-2 wiki text. So on the desktop, right? This is so you can see here in the path, home, your user account, desktop. It created this based on the information you gave it on the trainer. So on the trainer code, you wrote on here, model checkpoint. So the model checkpoint is just GPT-2, is what you downloaded from. There, model checkpoint is GPT-2. And then you specified wiki text so-and-so. So then that is exactly this one over here. So if you can see, these are the checkpoints that it's creating, and they're big, okay? So it's, you know, it's going to start to fill things up. So if you run out of memory, it'll just die, basically. So, oops, sorry. 20 gigs already. You can see on just this one job, it's already gone up by 6 gigs, okay? And it's really that part. I mean, you could go in there right now and start like deleting stuff and let it finish, right? So it's something we could do. So in theory, I mean, should I delete these? So I'm gonna delete. So let's see, desktop, GPT-2 wiki. So there's, you know, I can delete this one, that one. They're gone. So I can go to my quota, 17. So you see, I'm controlling that. These are tricks that you kind of have to like play with. As I said, read the documentation is probably the best thing. Find out what the limits are. As I said, this will be a problem. I don't think RAM would be a problem. You'll certainly have enough GPU power for the mini project. Okay, so it's at 17. I'm watching it. Still going. It's giving some training losses and validation losses. Okay, so it's at almost half. Well, maybe like a third, probably, right, of the iterations that it should do. And so this is basically what you would have to do for your assignment. Any questions, guys? Making sense? All right, so yeah, yeah, we'll, you know, basically you're doing a fine tuning of a project, right? Given the code that I gave you. But this is not RLHF, this is just regular fine tuning, basically. So I kind of want to see it to the end. So it's up to 19 again. I click on desktop, GPT-2 wiki, I've got 3 there. I'm gonna delete this one. Yeah, it's halfway there. Okay, so yeah, that's I don't really have anything else to show you of what else is to, yeah, this is to access the files, the interactive apps. I haven't tried that. Might take you to a GUI version of the desktop, I'm not sure. Scholar Shell, I showed you that. Read the documentation, it's probably a good idea. One, two. We're going. All right, so I think that concludes the discussion. I believe you guys are good to go, right? With this, if you have, so try it, try to run the code I gave you. As I said, you may need to install some libraries. Your data, maybe if you put it on GitHub and then you can retrieve it from there. Okay. I didn't think about that, how to load the data. Maybe there's an upload. Where was that? In the
Jupyter has one in the top right.
here?
Yeah, Jupyter,
This one?
yeah,
Okay, so this would upload the file. Okay, yeah, that's
on
actually
the side of the view or something.
so like I think I have like Iris here somewhere. Yeah, Iris CSV. Okay, upload. There it is, yeah. So yeah, so you should be then, this would be in the current working direct, thanks, Joey. So this would be in the current working directory and hopefully then, so that you can upload your files that way. Got it? All right, perfect. Let's see where it's at. It's at 4,000. 20 gigs. I'm gonna delete something. All right. So yeah, so that's kind of the demo for today of how to use the environment. The next thing we're going to do is we're just going to go over, finish up the theory on transformers. So I think we'll be able to finish that up today. I'll pick up with GPTs and then finish up with BERT basically. And all right, so I'm going to switch gears. So I think I'm going to just exit out of here. Oh, it's doing something. It's probably calculating the performance metrics. So it's got 1,500. Just going to let it run and see if it finishes. All right, so let's go to the notes. All right, so we were here, right? I'll just recap real quick. I know we went over all these concepts. You don't need to know like every single detail, okay? So there's the algorithm, and then there's a lot of like very technical things on how to make something work, right? So I'm not gonna ask you on the exam like very specific technical things, okay? But I do want you guys to know the gist of how it works. In particular, because I mean, transformers are difficult. I mean, They're very difficult, okay? But this is why I've given you this assignment so that, especially the first one, so that it demystifies them a little bit. All right, so I'll kind of pick up here. Basically, what I had said, we have this class GPT model, right? And this class is where everything is brought together, this diagram over here. So I kind of want you to understand that a transformer has an encoder and a decoder, and the GPT is only the decoder part of it. So just to recap, you get, sentences here and the same sentence on this other side, but they're shifted by one basically, and you're trying to predict, right? Teacher forcing means that you always give it the right sentence, the same sentence here and here from the train set. You don't let the GPT predict during training, because as you start to predict, you start to make errors, right? And so it's learning badly, if you will. It's making a bad prediction, and then it would learn from that bad prediction, and you don't want that. So teacher forcing is the concept within training. You give it the right data. Then in testing, obviously, it needs to predict a word that becomes input to the next prediction, and so on, right? That's what it's doing. Does that make sense? So that's an important concept. So then you have the sentences that go in, then they basically become represented as embeddings. Remember, I said that, so you convert them into integers, and then these integers, 3, 7, 55, whatever they are not what the transformer will look at. Instead, it'll look at a vector representation of those. So it's actually a simple concept. Every ID becomes a vector of size 512 in this case. And those values are initially random. Okay, so the values are initially random, and the transformer learns them actually. So the transformer learns them. So they are giant embedding machines in a sense, especially like the encoder here, all of this, and at the end, you get N40 by 512. This is the batch of sentences. This is the size of the number of subwords in there. And this is just each ID as a vector of size 512. That's it. Okay. So hopefully that makes sense, but it has learned from looking at all that text, the correlations, and so you have the representations there. Okay. So anyway, so that embedding goes through all the decoder layers, right? So you have 1, 2, 3, 4, 5, 6 totally equal encoder, decoder layers, and they take in n by 40 by 512 and produce n by 40 by 512. And that just keeps being changed and changed and changed until the final layer, where this is just a straight, normal feed-forward layer, like the ones you always use in deep learning, right? You got, that's basically what it is. So it's got like input is 784, like in MNIST, and the output is 100. That's it. Okay, but the difference here is that it's n by 40, no longer by 512. Instead, it's now n by 40 by size of vocabulary. So each of these tokens needs to be mapped once again to a word, right? Remember that in our example, we use letters, right? So the size of this was like 65, I believe. Okay, just check this thing, because it's gonna finish in a sec. 23. Just want to make sure it finishes without any issues. All right, so I think it'll finish with just with that. All right, so yeah, it should be finished in a sec. All right, so let's keep going. All right, so anyway, so that was kind of a review. Then we talked about this code already, so I went over all the basic things, right? So the IDX is the data that comes in, right? Remember, in the forward function, remember this is the class GPT model. So we already talked about this one. This is the labels, right? The real data, right? Which is basically the output data shifted, okay? This gets converted. These are IDs that come in that become embeddings. okay? And then it just goes, the X goes through the blocks, the 6 blocks, then it goes through the feed forward layer, which is the last one. That notice I put the dimensions here, 40 by 65, because 65 is the vocabulary size. So we talked about that. I think I already described this. And I'm pretty sure we were at block, class block. So that's where we left off. Remember that class block just means each one of these 6 decoder layer blocks. These are basically what they look like inside. If we were doing the original encoder decoder, that one, remember that basically the encoder decoder takes in data from the encoder into the decoder, okay? But GPTs don't have an encoder and a decoder, they just have a decoder. Therefore, the decoder layer looks pretty much like the encoder layer. Do you guys see that? Because you don't need a way of using the output of the encoder. All right, so basically then it looks like this. You're effectively here, when you look at this, you're looking at an encoder layer or a GPT layer, either one. All right, so notice n by 40 by 512 goes in, n by 40 by 512 comes out. Pretty simple in that sense. But inside, there's gonna be 2 layers. One is the fully connected layer. This is not a problem, normal layer, right? But this is basically the most complex part of this whole thing, called a multi-head attention layer. So I'll explain this with like a diagram. Please ask questions if you have them. This is definitely where I'm going to ask you a few questions on the exam, as it is the important thing. But I'll give you the basic idea. It's actually somewhat interesting how it works. So the multi-head attention, right? So there's actually 8 multi-head attentions, okay, that are done. So this is the block here, right? The actual code. You know, there's the init part, of course, but this is the forward. The ln1 and ln2 are just normalizations. That's all that's happening there. So really what matters is that SA takes in X after normalization. What is this? X plus self SA of X. Remember, we gave this a name, the residual. This is really important. This is what allowed deep neural networks to be very deep. So it's actually a very important concept that's so simple to implement, right? So the X goes into the SA, plus X, and that is the residual, and then that X, notice, just goes into the feed forward. So SA is what? That's the question. If you notice over here, SA will be initialized as the multi-head attention. So this is probably the most complicated class of the transformer. And then FFW gets initialized by feed forward, which is pretty easy. So the total opposite of. So let's take a look then at the multi-head attention over here, right? The multi-head attention actually is just invoking yet another class called the H class here, which is the head class. Okay, so you have an additional class called the heads. So the attention head is actually where attention happens, but it's just a block that you repeat 8 times. So I think I gave the analogy that, you know, if I have a problem, right, and I try to solve it myself, it would be better if I just had 8 people think about it, right? So each of you is an attention head, each of you gets the exact same X, and each of you thinks about the problem in a different way, which basically means you calculate different weights in a different way. And then you have an output, you have an output, you have an output, and all those outputs are put back together. You see that? And that's it. That's what the attention head is. If you notice, it's very interesting. Here, this is just a list in Python, right? So what is happening is this is a list comprehension. So you just say for head and self heads, right? So self heads is this one over here, initialized, right? As a NN module list, okay? That's important because this is a PyTorch concept, but at the end of the day is just what? 8 heads. They take an input, give an output, okay? That's it. So the input should be n by 40 by 512, but interestingly, the output of each head is n by 40 by 64. It could have been n by 40 by 512, but then you would have 8 tensors of size n by 40 by 512. How much is 512 times 8? You guys know? Whatever that is large, right? It's almost 5,000, 4,000. So the problem with that, I'm pretty sure this was just a decision they made at Google when they first doing this. They just said, okay, we want the 8 heads. They get in n by 40 by 512, and now it's intuitive that we would get an output at n by 40 by 512, but we have 8 tensors. So all of our entire code has been very elegant. It's always n by 40 by 512 goes in, n by 40 by 512 comes out. Do you see that? It's very nice everywhere. Except now you would have a tensor. Once you concatenate all 8, you would have a tensor that is n by 40 by 512 times 8, almost 4,000, a much larger tensor. And they didn't want that. So they just said, well, that's very simple. Let's just compress it. So what they do is, you have to, if you add more heads or what, when you start changing things, you have to think of these parameters. So in this case, what happens is, if you notice, they made each output 64. Why 64? Because there's 8. So 64 times 8 is what? 512. So all they decided to do is, let's just concatenate it. So a good analogy to this would be if you're trying to understand language, but you want to use multimodal text and speech. So you would put a vector of the text part and then just concatenate a vector of the speech part. And that becomes your whole vector. You see that? You can do that. So that's basically what they do. With the math, they force the model so that the inputs are n by 40 by 512, the outputs are n by 40 by 64, but then they just concatenate all 8 to create a tensor that is n by 40 by 512 once again. So they get to look at so 8 heads get to look at the thing, but also it's compressed a little. So it has to be more efficient even, and then it's concatenated. Do you see that? So that's basically what's happening here. So you create the 8 heads. We need to look at the 8 heads output, but basically it creates the 8 heads, and then here, so this is just the instantiation of the 8 heads, right? And then if you notice over here in the forward function, each head gets an X. Do you see that? Each head, so the X that has the data goes into a head. There's 8 of them in there. They work independently. So they basically get an X, but they're all 8 are independent. And then notice they're put in a list, and that list is what? Torch cat is torch concatenate. So it just gets concatenated so that the output of this, and it just specifies the last dimension where you concatenate them, which makes sense, right? So you're going to end up from n by 40 by 64 to n by 40 by 512 because you're concatenating all 8. Got it? That might be like the most tricky part of understanding, but yeah. So once you have that, out just becomes your n by 40 by 512, and that goes into project here, which is just the linear function. Okay, so that's basically that part here. All of this, it's explained in there, so you can see the multiplications right there. Now feed forward. I've used head, but we haven't actually looked at head, right? So we still need to look at head. That's actually where the attention happens. So that's the last piece of this, okay? It's like saving the best for last, right? So that part we still need to look at, but we'll do that in a sec. And then the other function in here, forward, sorry, what is it? Project, yeah, project gets instantiated as a linear, okay? So then, no, sorry, I'm getting these confused. So project is just inside. Okay, so project block, each block has a multi-head attention and has this fully connected is what you get from the multi-head. Yeah, so it's this. So then here in multi-head attention, you also have a linear. That's what it is. Okay, so in multi-head attention, inside of it, you also have another linear. After the n by 40 by 512, it just it goes in to this other one. Okay, and it's just a 512 by 512 basically. That's another layer. Okay, which makes sense, yeah. And then if we look at the feed forward, where is that one? Yeah, feed forward takes in 512 here. Now notice that what feed forward does is it takes 512, it produces 512, but in between it does 512 times 4. Do you see that? So it goes in as 512, it gets made bigger, and then from bigger it goes back to small. Do you guys see that? Why is that? It's just another layer to give the neural network to think about. You see what I'm saying? So it's another pass at it where they just, do this. This is another layer that is added in between, basically. Okay? And so hopefully that made sense. So I did the concatenation here, right? Then it goes to that feed forward. So at the end, you get the n by 40 by 512. So the trick is now, the last thing to look at is what is ahead, right? So we have to look at the last class, which should be that one. This is the attention mechanism, okay? This is the attention mechanism that's happening here. There are some technical things happening here, but in general, there's I'll just address the very basic ones. So the head here, if you notice, you have these functions, key, query, and value, okay? And these key queries and values take in X. So X is like the sentence, right? So you have a sentence that's coming in, but as I said to you guys before, you don't actually compare the sentence. Instead, you compare the sentence going into key to produce something called K. So you end up comparing K with Q. You see that? That's what you compare. But really, if you think about it, you're comparing X to X because it's the input to both of them. So if we look at Q and query, what are they exactly? Basically, you're just mapping from 512 to 64, right? And on the last dimension, only on the last dimension, okay? So you still have n by 40 by 512. Now it becomes n by 40 by 64. This is the compression part, okay? That's going to happen here. So when you do this operation, so notice again, you get X goes into key and query to create Q and K and Q, and then basically you perform this operation here. And this operation is what creates the 40 by 40, okay? This is the operation that creates the 40 by 40. So for this part, I'm going to switch to the whiteboard, okay? Because this is the most tricky part. Okay, so, all right. So you want to do the attention. The attention is really why 40 by 40? Because your sentences are size 40, correct? Size 40. So this is the cat is sleeping. You see that? So what you're going to end up doing here, what everyone will say is the cat is sleeping, and then the cat is sleeping, right? That's why this is 40 by 40. Do you see that? So that's the intuition of this, is that the cat is sleeping on its tail. They don't like that? All right, so on its tail. Right, so what is it going to, what is the purpose of the attention mechanism? The purpose of the attention mechanism is to correlate that cat and tail are what? Related. Do you see that? So it's going to then here find a strength between these two words of, let's say, 0.8. That's the point of the attention. It looks at things, and as it starts to see a lot of sentences, it's going to say, you know what? I associate cat and tail together. I give this a lot of strength. This number then is going to affect the embedding of cat and tail. So cat is going to have an embedding and tail is going to have an embedding, right? So the fact that there's a strength between these two values is going to change the values of cat and tail, because they're going to be related now. And that in itself tells you that it knows something about this. It's a feline, it's a type of an animal. Does that make sense, guys? So that's what's happening with the attention mechanism. The only thing is, as I said, what you compare is actually Q and K, not directly the words, all right? And so basically you can think of it as Q and K are just X. So it's the original sentence, but what do you do to it? Do you see that? You're just giving it a little bit more. It's passing like through another layer, basically, of the neural network. It's another embedding. It gives it a little bit more flexibility, right? So instead of comparing directly the x's, it's the vector of x's that's going in, the embeddings, right? Multiplied times W and, another neural network layer, basically. Does this make sense? So this, and and also it's 64 and all of that. And then there's a final V1 that basically the multiplication of V just takes it back to 64 from this shape here. So it comes out. So it goes, if we go over here, you can think of X as coming into the attention layer, right? And becoming 40 by 40 by becoming Q and K. And then you have an additional V, which is also made of X. So X goes here, X goes here, X goes here. And this final operation will produce N by 40 by 64. Right? Yeah, so it's basically a whole bunch of matrix multiplications that are happening there. Okay? So you have N by 40 by 512. That's the original X. This becomes Q and K, which are going to be N by 40 by 64. You perform a matrix multiplication between Q and K. So you do Q times K, and this is a linear algebra operation with the transpose, and this produces 40 by 40. And that's actually where the attention is happening. In this multiplication, you're comparing the Q and the K. And then this one then, which is called WEI in the code, gets multiplied again times this thing called V, where V is also X originally. Okay, so it's X originally, and this just changes the shape back out to N by 40 by 64. And that is the output of the attention. So it comes in as n by 40 by 512. It gets compressed into n by 40 by 64 twice. Remember, it's the same sentence. It just gets renamed as Q and K. Then you perform this operation. That creates the 40 by 40, which is where the actual attention happens. And it's called way. And then way is multiplied times V to become n by 40 by 64. And that's the output. Now, remember, all of this is just neural network operations, right? So you define the dimensions, 40 by 40, but the values are weights that are going to be learned by the transformer. That's the whole trick of it, is that you set up all these multiplications of all these shapes. All these multiplications are really network, neural networks, and they're weights that you are learning. So remember this, right? So when you have something like this, right? You have, let's say something like that, something like that, something like that. That's a neural network, correct? That's a neural network. This is X. This is Y. What is this one? That's W. You see that? So that's a neural net. So when I say that I do a matrix multiplication, what am I saying? That, correct? X times W is a matrix multiplication. That becomes Y, this one over here. Do you see that? And the B is just plus B. So ultimately, when I say that I do this matrix multiplication over here, you can think of it as a neural network calculation, right? So all of this is neural network calculation. All of it is weights that you're learning, but you're just performing these operations, okay? But as I said, the key thing is X comes in, it gets converted into n by 40 by 64, Q and K. These are now the 40s, and this creates the attention matrix way, okay? So going back to this example, Q and K really have the words in there, just not directly. It's like they're encoded one additional layer, okay? And you perform all the multiplications, but you don't know the weights, right? So the weights are the thing that gets learned, remember. And when you do this, that's basically filling in the values in here in the attention matrix. Okay, so what's important about this is remember that what you're trying to figure out is the embedding of something, right? So I've given this example several times. So I have the word bank. We know for sure it's going to have an embedding of size 512. But what is it going to be? And we can have multiple types of bank, right? So we can have bank for bank of the river, bank and river. We also have bank of robbers, right? So money. Do you see that? So when you have the attention mechanism, right, you're going to have bank and river over here. And so it's going to learn that these two are correlated. So then that's going to dictate what the embedding of bank is going to be. It's going to be a specific embedding. Like I'm going to say that, this is a river. So this is going to be like 0.5, 0.7, and this is 0.00, just to give you an example. But in another case, I'm going to have bank of money. So in that case, even though river could be there, it's going to learn money. So this one over here, the eraser, would actually be So this one over here would probably be like 0.1. And because it's the sentence, the context is about money and bank, this would be something like 0.8. So this embedding is different. That's what is really important to understand is that maybe this one would be 0.1, 0.2, and over here is like 0.7, 0.8. Ultimately, this is what's happening in the attention mechanism, that it's producing embeddings that are different depending on the context. So that's why it says it's all about the context. It knows what it's looking at, right? And that's basically the idea. All right, so whenever it sees sentences with bank and money and things like that, it does a type of an embedding. Whenever it sees bank and rivers, it does another type of embedding. That's what attention does. So by looking at these values inside, remember that this is at the end of the day driving the output embeddings that are coming out. Why? Because it's n by 40. Remember, maybe this will make sense. It comes in as n by 40 by 512. It comes out as n by 40 by 512 at the very end of the model. But the values that are here for each of these 40, these 512, have been dictated by what happens in this attention mechanism. Because it found the correlation between these two. So it says, okay, I know what this output should be versus another one. Any questions on that idea, guys? Does that make sense? All right. So anyway, so that's the attention. Okay. So let me start here. So let me go back to the code. Okay, so that's the code that is happening here basically for the attention mechanism. And this is explained there. And then after that, that's the last class, I think. That was the head class. Okay, and if you notice here, the output is B by 40 by 64. Remember that there's 8 of these that will get concatenated to create B by 40 by 512. Okay, and that's it. That's the end of that's the description of all the classes in the GPT. Finally, here you just instantiate the model and you start the training basically. And this is the training function. Okay, as you can see, basically, you grab a batch of data, right? The input and output just shifted, and you run M with the data, right? So the input sentence and the output sentence, and this gives you the losses basically. And then at the end, just like we did in 520, you zero out the grad, loss backward, and optimize your stuff. And this updates the weights basically of the model. So the model gets an input, runs through all, have some weights, predicts something, compare to the real, back propagate, update the weights. And it keeps doing that until, given a prediction, it's giving the right output, basically. All right, so that's the training function. Yeah, and then after that, you can, once it's trained, you can just use it with mgenerate. You decode the outputs, basically, and that's it. That's the description of the GPT. Questions? No questions? Crystal clear? All right. Hopefully it is. All right. Well, anyway, so that's it's a complicated model. All right, so it's 6:13. This is a good stopping point. Let's take a 10-minute break. We'll come back at 6:23, and then we'll just discuss BERT models basically. I'm not, the code is described now, so I'll just do more of an overview of them. All right. So let's take a 10-minute break.